Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today as it is every day here in my stumbling, bumbling, mumbling virtual classroom. I almost ran over my own words there. Okay, guys, we are going to cubic functions. We are going to transform them and write their equations and describe transformations, and we'll start by graphing the parent function and seeing where everything goes from there, see how it's an odd function and things like that. If you came from my last stuff regarding transformations of general functions, that's good. At the very end, we talked about graphing quadratics in a way. They were a little confusing, and we're going to get into some of that confusion again. I've been dealing with it with my students a little on the quadratics front, and now we're going to the cubics. Just a heads up, if you didn't watch that video, or if you don't understand the thing about the whole what A, B, H, and K do with the graph, I'm going to talk about them kind of lightly, and then I'm going to go into the problems. I'm playing under the assumption that you know something, a little bit about them. You have some familiarity, and with that little bit of familiarity, we can take the rest of the way and make sense of it. If you haven't seen it before, you might get stumbled with it, all right? So anyway, let's go ahead and get started. I have several, I think like 17 or so problems to do, but some I think will go kind of fast after we, get a few knocked out of here. Now, we're not transforming just yet, guys. They're going to have us graph the parent function f of x equals x cubed, and then we're going to answer some of these questions based on it. Now, some of these things I haven't really covered in my series of videos just yet. I am actually going to go... This is technically a section ahead of what the inverse function section thing is, where we start to describe things regarding domain and range. But hopefully at this level you know something about domain, range, and end behavior, and it'll probably make sense when I mention them, even if you don't know how to fully answer them all just yet right now, but you'll understand what they mean. Okay, so here we go. Let's graph f of x equals x cubed. Now I'm going to do it without a table, but I'm going to do it understanding how a table would do it. Plug in numbers, get out values. So if I substituted in the following for x, right? We're going to cube. Let's cube 0 and 1 and 2 and -1 and -2 and plot them on a graph. So 0 cubed is 0. 1 cubed is 1 times 1 times 1, which is 1. 2 cubed is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So we get that very sharp increase there. Obviously not linear. And then let me kind of put myself on the other side for this one, just because of how we're going to answer these, at least for now. I'm sure I'm just in the way in general. Now, -1 cubed. When we squared -1, we got a +1, because a negative times a negative was a positive. But now we're cubing it. -1 times -1 is +1 times -1 is -1. So now we get to a -1 value. And then -2 cubed is going to be -8 for the same kind of reason that -1 cubed is a -1. So there is a bit of familiarity with, oh, the 2 cubed is 8, but now it's on the negative side. And then we get this graph right here. And, 3 cubed is 27. This isn't as well curved as I'd like for it to be. 3 cubed is 27. 4 cubed is 64. You can see how much it shoots up in the end. But this is basic cubic function. This is the parent function of a cubic, and yeah, we're going to be transforming this thing. You got to think of 1128 now. 1128, maybe 327. We cube our values, and we might vertically stretch or compress or reflect or translate some things. Now, cubics don't have vertexes, by the way, but this thing here I'm going to call the center. Center, when we start transforming things, is what we're going to be moving, because it starts at the origin when there's no h and k present. But eventually that center is going to be moving, and that's where we're going to base things off of. Okay, state the functions domain and range. Now, domain and range have to do with how far left and right these graphs go. Domain is how far left and right these graphs go. Range is how far up and down these graphs go. Now, I'm going to answer range first, only because it's probably more clearly visible to you guys. This graph clearly with the arrows shows that it goes up forever, and it clearly shows with this arrow that it goes down forever. This hits all real numbers for range, so I'm just going to say all real numbers. There are other ways to write it, from negative to positive infinity. There's an all real number symbol, things like that, but all real numbers for range. Domain. This is a little harder for you to see because you see so much that it goes up and down, but don't forget the fact, guys, that it is going left and right. As it's going up, see, you can see it's going right here, and as it's going more up right here, it is still going right. I mean, not very much, but x equals 3, y is going to be 27. X equals 4, y is going to be 64. The point is, x can still equal 4. And x equals 5, y is 125. X is 6, y is 216. X is 7, y is 343. X is 8, y is 524. Yeah, x is 9, y is 729, x is 10, y is 1000. It keeps going right. It might be going up a lot more than it's going right, but it's still going right. I can plug in a trillion in for x, and I will get a massive y value. But I can still have a trillion for x. It may be going up, but it is going right. And if it's going right, that means and if it goes right forever, there's no restriction on x for me going right. There's no restriction on me going x. It might go down forever, but it's also going left forever at the same time. This is an all real number domain. This is an all real number domain. Don't confuse the idea that just because it's going down and up much more sharply than it's going left and right, that it's not still going left and right. You can still plug in any x value that you like under the sun here, and there's no limitation from negative to positive infinity. And that's the point. All right, identify the function's end behavior. What this asks is, when we go forever right, where do we find our y values? And in this case, when we go forever right, as we can go forever right, we find the y values going forever up, forever toward positive infinity. As we go toward positive infinity in the x direction, we're also going toward positive infinity in the y direction. So I'll say, as x approaches positive infinity, y is approaching positive infinity. And then the end behavior the other direction, as we go forever left, as x approaches negative infinity, as we go forever left here, we find our y values going forever down. The y's are approaching negative infinity, because in this all real number domain, we can go forever right, and we see ourselves going forever up, and then forever left, forever down. That's what end behavior means. X and y intercepts, where do they cross the x-axis? The x-intercept, it crosses at 0, 0, so the x-intercept is 0. The y-intercept, it crosses at 0, 0, so the y-intercept is 0, and that's it. When it crosses through the origin, that is your only y-intercept, and that was our only x-intercept. There are some cubic functions that can do like this kind of thing, so you can have multiple x-intercepts, but not this one. And not the ones we're going to do here today, because they're, a couple videos from now, we're going to see ones that have boop, 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 and we got to know about end behavior, domain, and range, things like that. All right, identify the intervals where the function has positive values and where it has negative values. When they're talking about intervals, they mean what values of x do we have positive y's and negative y's. So where on x are y values positive, where on x are y values negative. The y values are positive when we're over here, right? These are positive y values. They're above the x-axis here. And those are the values when we're on x values that are to the right of 0. Right? As we go more to the right, the y values will go even more positive. Anything to the right of 0, we're getting positive y values there. So the way that we state that is the positive interval is every value of x that is greater than 0. When x is 0, y is 0. That's not positive or negative. Any x value that's greater than 0, like 1 and 2 and 3 and 4, all those will give you positive y values. The negative y values come at the x values like -1 and -2 and -3. Those when x is less than 0, when x is negative numbers. So the negative y values occur when x is less than 0. And this is just, I won't say coincidence, but it just happened to be that positive is when x was positive and negative when x was negative. If the graph went this way, which we'll see those, this case the y values are positive when x is negative, less than 0, and then the y values are negative when x is greater than 0. So that would be backwards. Just make sure you know that when I say negative, I'm referring to the y's, and obviously I'm referring to x's there, and there it is. Okay, identify the intervals where the function is increasing and where it is decreasing. This function is kind of technically increasing forever. There's a point, and I could clean up this graph a lot more. I think I want to try to. This graph technically does a thing right at 0, 0 where it plateaus. The graph is probably better served to be a little curved more like this right here, where it has a really sharp curve kind of later down the line, but at this point it really flattens out and it plateaus right there. You get a slope of 0 at 0. You get a straight horizontal line just at one single point at 0, 0, right here, right there. It flattens out. The rest of the time it's increasing, and I say increasing as in when we go right, we're going up. It's increasing here, it's increasing here, but right at 0, it flattens out. Now, some people say, and by say some people, I mean math instructors, math books, the math gods say that a plateau can be considered still continuing the same direction that it was on, or something when you hit a relative max or min that it's still increasing or decreasing at that spot. So one thing I can say for sure is this is never decreasing. And one thing I can say for sure is it's definitely increasing anywhere that is not x equals 0. And some people will state that it's also increasing at x equals 0. For the sake of being unique, I'm going to go ahead and say that it's not increasing at x equals 0. It is flat. And it's increasing everywhere else. It's definitely not decreasing there. A decrease would be as if it went down like that as x increased. But at where it flattens out here and here, I don't call those increases or decreases personally. Calculus books are accepting of it, but they are not requiring of it. So it's increasing everywhere from when x is less than 0, unionized when x is greater than 0. There are a lot of different ways we can put that. The union means this or this. Or when x does not equal 0. We can just say that, when x does not equal 0. It's constant when x equals 0. It's neither increasing nor decreasing at that point there. Flat line, constant. Okay, you can use interval notation as well, but they didn't ask us to do that, and that's a whole different thing to mention. Tell whether the function is even, odd, or neither. Explain. If we look at the graph, you might be able to tell that this thing has rotational symmetry, that point symmetry, that if I rotate this thing 180 degrees as it goes through the origin there and does everything, I get the same graph back out as I have right now. That's something that says odd function. Odd function. Another way of doing that is by going ahead and substituting in f of negative x into this, and we get negative x cubed, which is literally negative x cubed. So that is an instance of an odd function as well. Odd functions have an instance where f of negative x is the opposite of f of x, basically stating that from whatever x, y values I get, when I take the opposite of x, I get the opposite of y, which is true. 1, 1, negative 1, negative 1. 2, 8, negative 2, negative 8. That's what an odd function does. This explanation is good enough for me right here, but all that stuff works out. And, you know, the way the odd functions work is their graphs have some sort of symmetry. Not across the y-axis, not across the x-axis, kind of across both. The y and x makes it symmetrical across the origin. You reflect your graph across the origin, 0, 0. That's what odd functions do. Even functions reflect across the y-axis, only there. Neither even nor odd, it's harder to find a reflection to them. I guess they can exist, but it's hard to find the reflection across those. All right, here we go. That was just one problem, but that was the long one. But we have to do everything based off that parent function now. So the parent function is x cubed. Now we're going to take that parent function, f of x equals x cubed, and we're going to go ahead and transform it. This is where you have to understand some of the stuff that I spoke of before. So what we're doing here is, here's the general, let me bring myself back to this other side. Here's the general form of some g of x transformation based on some a, b, h, and k. G of x equals a times, g of x equals a times f of 1 over b times the quantity x minus h plus k. Now, our f of x is x cubed. So what we're going to do here is our g of x in this form is going to be a times 1 over b times x minus h quantity cubed plus k. You can put it that way if you'd like to. It's kind of up to you on how you want to go about that. Oh, hang on. We got to cube the b as well. Quantity cubed plus k. So that's that form right there. And what we're going to be doing is we're going to be transforming these things. You got to know where all these things appear and what they all mean in their own instance. We got to poke into what a, b, h, and k are, or what the values are here, and also how they work in the transformations. A means what kind of vertical stretch factors or compression factors there are. I'll put VSF as just a very short version of it. Vertical stretch factors, vertical compression factors, and vertical reflections. B is horizontal stretch factors, horizontal compression factors, and horizontal reflections. H is a horizontal translation, and K is a vertical translation, I should say, is a vertical translation. Now the HK is your center. It's your center value. That's where that part that I was talking about right here. This is the center portion. It's not a vertex anymore, but that's the part that we're going to be moving and starting from. So understanding this graph right here is going to be truly important for that, knowing how this graph looks. Okay, so how are these related to these? Now, they're only making us do one thing at a time here. So like x minus 4 quantity cubed, only one value's changed. And it looks like in the x minus h form there, it looks like your h is 4. Now, if I wrote all the other ones, you know, a is 1 and b is 1 and k is 0. That's what makes those disappear. 1 times anything is itself. 1 divided by anything is 1 times anything is itself. And anything plus 0 is itself. So, you know, A, B, and K, A and B are 1, K is 0, means those aren't changing. We're not vertically stretching, compressing, or reflecting. We're not horizontally stretching, compressing, or reflecting. And we're not vertically translating. We are only horizontally translating. That's where H is 4. Woohoo, H is 4. That's where H is 4. And we get to say, translate 4 units to the right. Now again, if you're confused by this, it's very likely that you didn't use these formulas from before, at least specifically this one right here. You got to check out my other video for that, or look at some instruction stuff for that to help you best. Okay. All right, g of x equals negative 5x cubed. This is in reference to our a value. Because this thing is outside of the cubed quantity, right? This is negative 5 times x cubed, just the x is being cubed. The a is negative 5. And with a being negative, that does mean that there is a vertical reflection here. A vertical reflection means we're reflecting across the x-axis here. So there are two things that are happening. Number one, we are reflecting this graph across the x-axis. That would take a graph such as this one right here, and flipping it over would end up making it look like it would go this way. And actually, reflecting across the y-axis, you'd get the same exact look. That's why it's not an even function. But reflecting across the x-axis, that's the look that you'd get. That's what vertically flipping it over does. And then we also vertically stretch this by a factor of 5. Everything becomes 5 times taller at the same x values. So vertically stretch by a factor of 5. And I just say 5, not negative 5. The negative had to do with the reflection. We already took care of that portion. All right, two more, numbers 4 and 5. Looks like we're going to hit the all the different parameters here. We've hit h and a. Now we're about to hit k here. So we cube our function, and then we add 2 to it, and that's vertically translating this thing. K is 2. A positive 2 means we are translating this thing 2 units upward. Now, by the way, I want to go back to h really quickly here. Why was h positive 4 and not negative 4? Because the formula has an x minus h in it already. We're subtracting h, we're subtracting 4, that must mean h was 4. This 2 is positive, but the formula has a plus k in it as well. So if we're adding k and we're adding 2, that means k is 2 and positive 2 there. Translate 2 units up. Last one here, g of x equals the quantity 3x cubed. There are 2 different ways you can do this, and actually, I don't know which one's going to be easier for you. I don't know. I'm going to start by talking about the b value here. Now, b is not 3. I know that we look at b right here inside the function thing, and we're saying, all right, it's inside, there's a 3 inside, so b is 3. But you got to be careful, guys, because the formula talks about 1 over b, and it's for a good reason. The same reason as the minus h. There's something about inversions when you take the function. It's about what plugs in for x. But there's a good reason for it. Now, the idea, though, it is a 1 over b. The 1 over b is 3, not b. So what is b? What do you have to divide 1 by to get 3? You actually have to divide it by 1/3. If you multiply both sides by b and divide both sides by 3, you're going to actually get b is 1/3. So b is 1/3, not 3, and the 1/3 has to do with a horizontal compression, which states that we horizontally compress by a factor of 1/3. All your x values get thirded. You divide them by 3 as the y values stay the same. Horizontally compressed by a factor of 1/3. Now there is a vertical equivalent to this, and I'm more privy to doing vertical stretches and compressions than I am horizontal. Like, I would never turn a vertical into a horizontal, but I might turn a horizontal into a vertical. So what you could also do, guys, is you could also take this 3x cubed, quantity cubed, and turn it into 3 cubed, which is 27 times that x cubed right there, suddenly this turned into an a value, and the a value is 27. So the equivalent of horizontally compressing this graph by a factor of 1/3, taking the x's and dividing them by 3 to keep the same y values, is vertically stretching this by a factor of 27. Vertically stretch by a factor of 27, which means take the y values and make them 27 times taller at the same x values. These are the same thing. I know that seems weird, maybe you're not understanding what that means yet, but yes, these do run in tandem with each other. One or the other, not both. You don't horizontally compress and vertically stretch. Either you vertically stretch this by 27 or horizontally compress by 1/3, and you'd get the same graph regardless there. So either or, you would get the same thing. It depends on how you want to pull it off, either with the A or with the B. Just depends on your idea of the transformation, but there it is. I say for the sake of the exercise, you probably stick with B, but you know. All right, let's move forward here. Oh, we do have some more here. Okay, let's keep going. So here we go. I'm gonna go a lot faster now. So this is an H value. What do we have to subtract to get a +1? Looks like you got to subtract a -1. That means H is -1, which means horizontally translate. You know, I don't even have to say horizontally. It means translate. I don't think I did before. 1 unit. Once I say left, you know that's horizontal, right? 1 unit left, like that. All right, g of x equals 1/4 x cubed. That's our a value. Our a is 1/4, which means we're dividing by 4. We're compressing by a factor of 1/4. I do have to mention vertically here because no other thing kind of tells us that. This is vertically compressed by a factor of 1/4. Now the 1/4 tells you it's compression. I think I mentioned in my other video. It's just a courtesy to say compress. You could technically, I guess, still say stretch. The point is the 1/4 takes care of it. But compression is a courtesy letting you know, hey, it is a shrink. All right. This is a k value here. Once again, it's outside of the thing that's being cubed here. So that's a k of -3. Okay, so we're going to go ahead and translate that. 3 units down because it's negative on k. 3 units down. And lastly, g of x is -2/3. Okay, once again, it's a little confusing with this. B isn't -2/3. 1/b is -2/3. So let's work on this one. Oh, you know what? This is a proportion now. We could cross multiply. B times -2 and 3 times 1 gives us 3 equals -2b. And divide both sides by -2, you get b is -3/2. Really what you're doing, guys, is you're reciprocating what's here. You flip it over. The 3 turn into a 1/3, the -2/3 turns into a -3/2. There's b. Now that is a stretch. That is a stretch because it is more than 1. Well, it's negative. We'll talk about that. But it's a stretch because it's a number that's more than 1. It's 1.5. Everything becomes 1.5 times wider with that. But two things are happening, guys. It also is negative. So we are going to horizontally... Excuse me, we're going to not horizontally reflect. We're going to reflect across the y-axis. Reflect across the y-axis, which is a different graph for a cubic. I'm sure we're going to look at them when we draw them. And we are also going to horizontally stretch by a factor of 3/2. Stretch by a factor of 3/2. Okay, so that is that one right there. And now we're going to do some with those graphs here as well. Identify the transformations of the graphs f of x equals x cubed that produce the graph of the given function g of x. Then graph g of x on the same coordinate plane as the graph of f of x by applying the transformations of the reference points -1, -1, 0, 0, and 1, 1. So it's saying fit these points where you can after the things are transformed in relation to the original f of x parent function. And this is what the original graph looks like here. See that they really did plateau this a lot better than I did. It doesn't increase nor decrease right at 0, 0. It flattens out right at that point, but it's increasing the rest of the way. Anyway, that's f of x. G of x, what's it doing here? Well, we start with a, I won't say a difficult one, but we start with b. That's not always my fan favorite. B inside of here, remember it's all about 1/b. 1/b means that b is 3. That means we are, I'm going to say it, not write it, but we are horizontally stretching this by a factor of 3. Every x value becomes 3 times larger for the y value that it's at. So 0, 0, I triple the 0 on x and I still get 0 there. Nothing changes. 1, 1, I triple the 1 on x and that becomes 3. So 3, 1 instead of 1, 1. By the way, I think I'm going to mention the 2's for the sake of my students. I might not be able to graph them, but I am going to mention the 2's. -1, -1, we triple the x, and that becomes -3, -1. So again, at the same height, you're getting tripled the x values. It's stretched here. And to make sense of it, you know what? I might have to plot these other points just to make sense of it and how you're going to graph, because it's not a straight line, right? What happens next is there is a curve. And what does that look like? This original graph would have gone at 2, 8. You probably saw that on number 1. 5, 6, 7, 8. That's where that graph is going up to. But now we take that 2, 8, and we're going to triple it, triple the x, and we get 6, 8. So instead, it's going to go up here. So my new graph is actually going to be going all the way up there, you know, from that point, right? That's what that curve is going to kind of look like. Let me try that again, because I want to get the flat part here. So flat, and then that upward curve into that right there. So that's what that graph kind of does. Not that you have to know that for sure, like get that point, but I do want you to understand that it does curve up. It's not straight just because we can only fit these 3 points. And then there's -6, -8. Let's see. 6, 7, 8, and -6. It's probably down there. So this graph here does this on this side. Right? There's that curve to it. That's a lot bigger than they'd need us to do. But it's a horizontal stretch. If they want us to just keep the same height with the arrows, because that's as much as I can fit, I'm going to go ahead and give you those. But that's the nature of our curve, guys. That's what it's going to look like. After a horizontal stretch, this thing stretched 3 times as much as it would have before. All right, now 1/3 here. And what's the difference? There's a huge difference. 1's in parentheses, which means the whole thing gets cubed. The 1/3 here is not getting cubed. This is like our a value this time. This is an a of 1/3, which means, and it is 1/3, it's not 3, which means we are going to vertically compress by a factor of 3, vertically. Everything is going to become 1/3 of what it was before. And this is where I think it is kind of nice that I can take my 2, 8 and do something with it. So the x values stay the same, the y values become 1/3 of what they were before. 1/3 of 0 is 0. We get 1, 1. Let's take 1/3 of 1, which is 1/3. Not a beautiful kind of value there. None of these will be beautiful here. -1, -1. We take 1/3 of that, and we get -1/3 like that. And again, it's not straight. Let me give you the 2 value as well, so we can kind of make sense of that. Instead of 2, 8, because 8 is 2 cubed, we're going to do 1/3 of 8, which is 2 2/3. So 1, 2 2/3 like this right here. And then this is -2 and -2 2/3 right there. That'd be that point. I couldn't really fit the 3 cubed on the window, but to make sense of it, 3 cubed is 27, and 1/3 of 27 would have been 9. So this would have been 5, 6, 7, 8, 9 up here, as it would go down and get that graph, and then like -9, -6, -7, -8, -9, like that. And so that's vertically compressed. You can tell that it's going to be shorter than this graph at all those points right there. And yeah, let's go ahead and get those. Not perfect, but you know what? Whoever was. There we go. So there's the graph when it's vertically compressed by a factor of 1/3. It's shorter at those x values. There. All right, here we go. Looks like we got some translations to be had here. Now, I like to translate from this point here so I can then do my 1, 1, 2, 8 as I know I'm supposed to. So let's check this thing out. The h is 4, +4, and the k is -3, which tells me that I'm going to translate this thing 4 units right and 3 units down. So 1, 2, 3, 4, and down 1, 2, 3 like that. And then from there, guys, you plot all your other points. So from here, I would do 1, 1, and I could do 2, 8 as well. I don't know if it fits on here. Not quite. It's up there. But that would be the 1, 1, 2, 8 equivalent. There's no vertical stretch factor. It's just a 1. So or the stretch factor is 1. There's no change in it. And then -1, -1, and -2, -8. I'm not really going to fit that one. But you can see what this graph is now doing. It's just a translation. There is no stretch or compression. So to do the best I can here, not even close, to do the best I can here, I'm going to get a graph that kind of does that. That's a little bit better than, that's actually pretty good. All right, so there's that graph there, just a translation, but this thing, I could have just gone over this and just brought it down, but that's all right. All right, this one is just translations only one more time here. This is an h of -1 and a k of +2. Remember a -1 because we're subtracting the h there. So negative 1 comma 2 is right there. No change in anything. You know, they didn't ever have us reflect on these, which is a little too bad. I wanted you to look like what it looked like what it flipped over. But I got a 1, 1, 2, 8, you know, up there. Negative 1, negative 1, negative 2, negative 8. I can kind of fit that. I think that'd be just off the graph right here. So that graph now is going to come up and through. It's not good. I'm sorry. But there's the graph there. Kind of, yeah, we're at the half-hour mark, so I want to kind of finish. All right. I have just a few more problems, 4 more problems to do, and what we're going to do is write an equation based off the graph. Now, the first 2 times, I'm also going to show you an algebraic version of what we're going to do. But on top of that, I want to show you the way I can do it kind of on the fly. The first thing is recognizing that this is your HK, negative 2, negative 3. That's going to be important there. Your H is negative 2 and your K is negative 3. So with regard to this graph here, guys, the information we do know is that g of x equals 1 over b times x minus negative 2, that'll be x plus 2. And that'll get cubed. That all gets cubed, and then plus negative 3 is minus 3. So we're almost there. What we're missing is b. They want us to find a horizontal stretch, apparently, or compression. You know, they want us to find the horizontal change in this thing and find that b and make that work. The way you do this algebraically is you have other points on this graph that can represent x, y's. Remember, these are solutions to your equation. That's an x, that's a y, or that's an x, that's a y. You may substitute this in for x and this in for y in your equation here. Remember, g of x means y. And you can substitute, or you can substitute this in for x and this in for y, and you can compute things to then get b by itself. And honestly, I think that's above and beyond what I really want to do now that I think about it, because I'd have to cube b. I'd have to do a lot. So I think I'm probably, you know, I'll do it for this problem. You know what? I'll do it for this problem. But you're going to see why I can get a little, like, in with it. You know, I'm like, there's a better way. So you choose one of these x, y's. I'm going to choose this one on the right here because I have a positive 1. I want to do that. So here we go. So 1 for x, negative 2 for y. So the equation will now instead say negative 2 equals, I have 1 over b times 1 plus 2 quantity cubed and then minus 3. Okay? So that's negative 2 equals 1 over b times 3 quantity cubed minus 3. So that's 3 over b quantity cubed minus 3. So to cube that, I got to cube the 3 and I got to cube the b. 3 cubed is 27, b cubed is b cubed minus 3. I should have done this a long time ago, but I'm going to add 3 to both sides. Let me do that right now. I'm going to add 3 to both sides here. Negative 2 plus 3 is 1. There we go. Oh, I don't need to, there we go. So b cubed, if I multiply both sides by b cubed now, I get b cubed equals 27. And if I take the cube root of b cubed and the cube root of 27, I'll get b equals 3. So that's the b value there. I got b equals 3, which means my final answer is now going to be 1 over 3, boom, like that. And that would be the final result. So again, my goal was to get h, k, and b on that thing there. And there was a lot of algebra to get that thing done, to get b by itself. I substitute in my hk, and I substitute in an xy that's not my hk, and I can find the b value based on that. That's the only b value that gets me that xy alongside the other xy. Now, how else could have I done this? Well, I could have looked at the graph, and if you know what the ordinary parent function does with regard to 1, 1, 2, 8, and negative 1, negative 1, negative 2, negative 8, if you know the original parent function there, then you can tell that from this center, this 1, 1 got tripled into 3, 1. It got tripled. The horizontal got tripled. That's something you can notice. And if you do notice that, then you'll know that b is 3 right off the bat because the triplage of b equals 3. I am going to make sure to do that on some of the last problems there, but I'll do it on this one first this time, and then I'll go ahead and kind of let you know what's happening. So on this one, on number 15, we have an h of 1 and a k of 4. So we do know right now that our equation is g of x. This time they use a because they're talking about it's a vertical stretch. So we don't know a yet, but we do know that we have an x minus 1 quantity cubed plus 4. let's figure out what a is in this regard. One thing I know about a, guys, if you know that your original parent function would have gone this direction, like that, you know that a is negative. This has a reflection about it. So we do know it's a negative value. The other thing that you notice here is, there's a stretch. So instead of 1, 1, here, let me go down because now we know it's a reflection. It's a reflection. So 1, 1. No, we're now going 1, 3. 1, 3 instead of 1, 1. The 1 got tripled into the 3. That means a is 3. Well, negative 3. So that's me kind of saying, I'm letting you know already that that is the answer. Right there, negative 3. Well, actually, let me not write the negative 3 yet. We're going to take this thing, and let's go ahead and try and solve it algebraically. How did I get this negative 3 right there? Well, what you can do is you can take some x, y values, like such as this one. I'll just choose 2, 1. Plug 1 in for y and 2 in for x, and let's see if we get an a value of negative 3 by doing that. So 1 equals a times 2 minus 1 quantity cubed plus 4. Let's subtract 4 right now because we can, right? So minus 4, that's negative 3. Negative 3 equals a times 2 minus 1. 2 minus 1 is 1. 1 quantity cubed. Okay, this one wasn't as bad. You can see how the b one was a lot worse. 1 cubed is 1, so negative 3 is a. So that is the same a value we got, negative 3. So you can see sometimes it's a little easier, sometimes it's a little harder depending on the thing. I guess b is a lot harder because you got to cube it. There's something with a fraction, and it's just not as fun. But anyway, a is negative 3. We substitute negative 3 into here, and we are good. That is our equation that graphed that. All right, 2 more, numbers 16 and 17. Here we go. Let's find the b. This time I'm not going to do the algebra. Now we got to deal with decimals and stuff. That will just not be fun at all. So let's start with h and k. H, apparently, it's based on the center, right? H is 2, k is negative 1. H is k. H is 2, k is negative 1. Well, what's the b value? Well, we can see that, normally the graph would go this way. 1, 1, and 2, 8, and negative 1, like that. So because of this, we do know that there's reflection. There's a horizontal reflection. You could call it vertical as well, but we're talking about b. There's a reflection that goes this way. So instead, it would be going this way. 1, 1, and then 2, 8, and then negative 1, 1, 1 that way, and, the graph will go like that. So how much did it change here? What we do is we originally would go 1, 1. Now it looks like we want 1/2 1. And I know you see a 1.5, but that's the x value. I want to see how far it went from the center. Instead of going 1, 1, it went 1/2 1. It went half as much as it normally would, right? Half as much as it normally would. That means a horizontal compression of 1/2. Or in this case, because reflection, it's negative 1/2, and that's the b value. So your raw form of this equation would look like g of x equals 1 over negative 1/2 times x minus 2 quantity cubed minus 1. But 1 divided by negative 1/2 is negative 2, right? You take the reciprocal, you flip it, that gets negative 2. So g of x equals negative 2, oh my gosh, negative 2 times x minus 2 quantity cubed minus 1, like that. That is that's the end result right there on that b. Or for the whole function. All right, last one here. This is my last problem I'm going to do, and then we're all done. Number 17, a. Let's determine a based on this. Let's first figure out and the hk. The h is negative 1 because that's center. The k is 2. So what's happening here? Normally we'd go 1, 1, 2, 8, negative 1, negative 1, things like that. So instead of going 1, 1, it looks like we're going 1, 1/2. So it looks like we're taking half of our original thing there. And to confirm this, guys, I didn't do this for some of the other problems, but let's look at the 2, 8. 2, 8, 2, 1, 2, 3, 4, 5, 6, 7, 8 right here. What happened to it now? Now what happened is it ends up right here. Instead of 2, 2, 8, now it's going 2, 1, 2, 3, 4. Instead of 2, 8, it's 2, 4. That's half of 8. So it looks like we have a vertical compression of 1/2, and not negative 1/2. It's not flipped over. It's a 1/2 right there. So this equation would be g of x equals, the a's out in front, that's 1/2 times the quantity, x minus h is x plus 1 cubed, and then plus k is plus 2. So there it is. So that's me not plugging in those values into there. Otherwise, I could plug in 0 for x and 2.5 for y. You can see why I'm not as much a fan of that if I understand the stretch factor stuff and it helps me graph the other things without a table. All right, guys, so that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching this. I hope that it helped. I know it can get a little confusing, but alas, that is math for you. Thank you so much for watching, guys. Take care.